am Luis Anthony Ast, the Video Math Tutor, and welcome to Basic Math Lesson number 5, Factors, Multiples, and Divisibility. Let's get started. Numbers or variables being multiplied together are called factors, and the result of multiplication is called the product. A numerical example of this would be something like this. 7 times 5 equals 35. Factor times a factor equals a product. A single natural number A can be called a factor of another natural number B if there's a companion factor, call it C, such that the multiplication A times C equals B is true. In this previous example, we can state that 7 is a factor of 35. Why? Well, because there is a companion factor, 5, such that you can say 7 times 5 equals 35. Now, with the same token, you can say 5 is a factor of 35 because I can switch these around. And say, okay, right here, 5 times 7 is 35, so 5 is the factor and 7 will be the companion factor in this case. Now, are these the only factors of 35? Well, no. Let's see that. We can also say that 1 is a factor of 35 because 1 times a companion factor, 35, is 35. By the same token, again, I can switch these around and say 35 is a factor of itself because 35 times 1 is 35. By the way, factors are also called divisors. Why? Well, because they're numbers that would divide evenly and exactly into other numbers. When dealing with factors, we'll only be discussing the positive values. This is only for convenience and simplicity. A prime number, or just prime, is a natural number that has only two distinct factors, the number 1 and itself. You might be wondering, well, what about the number 1 itself? Is it prime? Well, no. See, it doesn't meet the definition of prime because it has to be two distinct numbers that are times each other. 1 is just multiplied by itself, so it only has one factor. For example, number 1, let's look at some numbers and see if they're prime or not. Well, by definition, it should be just two numbers times each other, and that's it. And one of them is 1, and the other one is just itself, and that has to give you the result that you're interested in. Well, in this case, 2, the only things that would give me 2 is 1 times 2. So, yeah, it's prime. How about 3? Well, 3 is just 1 times 3. So, yeah, it's prime. How about 5? Well, hey, we're on a roll here. I can just say 1 times 5. How about 4? Well, 4 I can say 1 times 4, so it must be prime also, right? Well, no, because see, I can actually think of another way of multiplying two numbers that will give me 4. 2 times 2 also gives you 4, so 4 is not prime. A natural number greater than 1 with 3 or more factors is called a composite number, or just composite. So going back to this example, 4 is a composite, whereas these right here are prime. Here is a list of all prime numbers that are less than 100. Now all other natural numbers, well, except 1, that are not in that list are automatically composites. Now you might be wondering, how did I get this list of prime numbers? Well, actually there's a procedure called the sieve of Eratosthenes, and it's a very systematic procedure that produces any prime numbers below a certain number. And it's on a companion video on the CD. For example, number 2, let's find out which of these are composite or not. 6, what do you think? Well, I know 1 times 6 is 6, but also 2 times 3 is 6. So disregarding order, I actually have 4 factors. 1, 2, 3, and 6. So 6 would be composite. How about 17? Well, the only things I can think of that will give you 17 is 1 times 17. There's nothing else that can do that. So it's actually considered prime. It only has 2 factors, 1 and itself. That's the definition of a prime number. What about 12? Well, there's a number of things you can do to get 12. 1 times 12 is 12. You can also do 2 times 6 is 12. And how about 3 times 4 equals 12? And you can also just switch these around. You can say 12 times 1, 6 times 2, 4 times 3. So there's quite a few factors. How many are there? Well, there's 1, 2, 3, 4, 6, and the number itself, 12. So because it has 3 or more factors, 12 is considered composite. Now the number 12 can be factored another way, using only prime numbers. Let's try this. See, 12 can be rewritten as 2 times 2 times 3. All this multiplied together will give you 12, and they happen to be all prime numbers. Now, another way of rewriting this is 2 times 2 is the same thing as saying 2 squared. So I can use some kind of exponent notation, 2 squared times 3. So these are a couple different ways of rewriting the factors that multiply to give you 12. And this leads up to our next definition. The prime factorization of a composite number is the product of 2 or more primes to get our composite number. The primes used for this factorization are called the prime factors. Exponents may be used for simplification. So going back here, we can say the prime factorization of 12 is 2 times 2 times 3, or you can say 2 squared times 3. Now I'd like to find the prime factorization of 36. To help me, I'm going to do something that's called a factor tree. Here's the procedure. I think of a couple numbers I'll multiply to give me 36. And there's lots of things. Well, the first that comes to mind is 6 times 6. So I'm going to branch out here and go 6 and 6. And now we think, well, what multiplies to give me 6? And again, you don't want to say 1 times 6. They need to be numbers besides the numbers themselves and 1. That's one of the rules. So let's see, 2 times 3. So let's put that on both of them. This is going to be 2, 3, 2, 3. Now can we break up 2's and 3's besides themselves and 1? Well, no, they're prime numbers. So my little rule is I actually like to circle the ones on the very bottom that I'm done with. Now again, the reason they call this a factor tree is because, well, it's actually officially an upside down factor tree. Think about it. This part up here is called the root. The 6's here are the branches because they're branching out past that. And the ones at the very end that have nothing coming out of them are called the leaves of the factor tree. Now based on this, see, right here is my answer. 36 is the same as 2 times 3 times 2 times 3. Now that's an answer, but traditionally we like to keep things in numerical order. So I'm going to rewrite that as 2 times 2 times 3 times 3. That is an answer. Now, some textbooks or professors want you to compact this using exponent notation. So another way of writing this is 2 squared times 3 squared. So either one is acceptable. Now a question does come up. Is there maybe perhaps another way of finding a prime factorization of something? Maybe I made a mistake, or maybe I didn't look into all possibilities with 36. Well, 36, no, that pretty much covers all your bases, but what if the number was bigger? Perhaps there's some other unusual way of trying to find this factor tree of this rather large number. So that's something I'm a little worried about, because maybe if I get an answer and it's different than, let's say, what the professor has. Well, actually, there's a special theorem that ensures us that there's only one way of doing this. Let's talk about that next. Every natural number greater than 1 can be expressed as a unique product of primes, not counting order. Oh, okay, so because of this theorem, it's now official, it's guaranteed. There really is just one way, without counting the order or maybe the notation. This really is the same thing as this. So there's just one way of breaking a number up into prime factors. Two numbers are said to be relatively prime or coprime if they have no prime factors in common. For example 4, let's verify that 18 and 55 are relatively prime. So to do that, let's find the factors. So let's break down 18. 18 is, how about 2 times 9? I can't break up 2 anymore, but 9 is really 3 times 3. So here are my factors. So it's 2 times 3 times 3. 55 can be factored which way? Well, now we have 5 times 11. Now look at this factor form and this one. Do they have any numbers in common? If they do, then they're not relatively prime. Well, because they're all completely different, they are relatively prime. The greatest common factor, or simply GCF, of 2 or more natural numbers is the largest natural number that is a factor of the given group of numbers. It is the largest whole number that will divide exactly into said group of numbers. By the way, the GCF is also called the greatest common divisor, or GCD. And that's actually the typical name that's used for graphing calculators. Let's find the GCF of 16 and 36. Well, to do that, let's list all the factors of each number. Now, not just the prime factors, all of them. So for 16, we have 1, 2, 4, 8, and 16. All these numbers multiplied in some way will give you 16. Like the 1 and 16, 2 and 8, 4 times 4. Let's do the same thing for 36. Well, we're going to have 1, 2, 3, 4, 6, 9, 12, 18, and the number itself, 36. Okay, again, this combination of these numbers will give you 36. Now let's look at the ones that are common factors to both. All right, well, let's take a look. We have 1 is a common factor in both of these. What else? 2 is a common factor to both. Anything else? Oh, right here. 4 is a common factor. And nothing else. So what can we conclude with this? Well, 4 is the greatest common factor. Okay, 1, 2, and 4 are all common factors, but GCF is the greatest, the biggest. So 4 is the largest that's in common to both. So that is our answer. So you can say GCF equals 4. What is the GCF between 16 and 36?
Our first step is to clear our display, then the math key and the right arrow. Now we press up and then enter. You could have also pressed 9, by the way. Let's input 16, comma, 36, close parentheses, and enter. And there's our answer, 4.
For our next question, we have, what is the GCF of 72, 600, and 420?
Let's clear our display, then math, right arrow, up arrow, and enter. Now let's input our numbers. 72, comma, 600, close parentheses, and enter. Now let's use this 24 with 420. So math, right arrow, up, and enter. 24, comma, 420, and close parentheses, and enter. And there's our answer, 12.
A multiple of a number is the answer you get when you multiply said number by any natural number. For example, the multiples of 2 are 2, 4, 6, 8, 10, and so on, since if we have a 2 and we multiply by a natural number, 1, 2, 3, 4, 5, and so on, our results are 2, 4, 6, 8, 10, and again, forever. Similarly, 5 would have multiples of 5, 10, 15, 20, 25, 30, and so on. A good way to think about multiples is just the results of your multiplication tables. Like for 2 is 2, 4, 6, 8, 10, 12, 3 is 3, 6, 9, 12, 15, 18, and so on. 5, like I just said. Okay, 10, 10, 20, 30, 40, and so on. On the calculator, there's actually a pretty slick way of putting multiples. It'll just spit them right out. First thing you do is input 0 in this thing, and then enter. Then you go plus, and then the number you want to find the multiples of. 2, for example. And then you keep hitting enter repeatedly as many times as you want, and you'll see the multiples just scroll on down on the display. Find the first 5 multiples of 2.
Our first step is to clear. Now we'll input the 0 and then enter. Now we'll go plus 2 and enter again. Now this is our first multiple. Now just keep pressing the enter key for as long as we need to. So enter, 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 and enter. So the first 5 multiples of 2 are 2, 4, 6, 8, and 10.
Find the first 6 multiples of 13.
Let's clear our display. Let's input 0 and then enter. Now plus 13 and enter. Now let's just continue entering. Enter, 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 and enter. So the first 6 multiples of 13 are 13, 26, 39, 52, 65, and 78.
By the way, for simplicity and convenience, we're only going to apply multiples to positive integers, in other words, natural numbers. Okay, no negatives. Don't go there. The least or lowest common multiple, the LCM, of a group of 2 or more numbers is the smallest natural number that is a multiple of all the numbers of the given group. For example 7, let's find the LCM between 8 and 12. Well, one way is we can just start listing the multiples of each. So here's some multiples of 8. Again, there is no end, they go on forever. And multiples of 12 are right here. And let's look at what ones are like in common to both. Well, looking at this, I can see, oh, right here, 24 is a common multiple. Are there any others? Well, yeah, there's right here, 48, and right here, 72 is another. And actually, we can actually go on forever. We can always find other things to have in common. But LCM means the least common. So of the 3 that we have so far, we want the lowest, the smallest one. So the LCM, in this case, is going to be 24. Now, it was kind of cumbersome to figure out these multiples. So there's got to be a better way of doing this. And yes, there is. And let's do that next. First step in finding the LCM is get factor trees of both 8 and 12. And here they are. Next, I'm going to write these numbers down. For the first one, I'm going to have 2 times 2 times 2. Now below this, I'm going to write down the factors of 12. But here's the deal. I'm going to line up like the proper numbers. Like if there's a 2 here, I'm going to put underneath the 2 over here. So 2 times, and here's another 2. So I'm just going to go underneath this 2 times. And here's a 3. Now I can't put the 3 underneath the 2. So I leave a little blank here, a little gap, and put the 3 right here. And then, see, I kind of like line these up like this. So the answer is going to be 2 times the 2 times this 2 times the 3. And lo and behold, there is our 24. For example 8, I want to find the LCM between 12, 45, and 50. So the first step, as you can guess, is you find the factor trees of each. And there they are. Now let's do this column approach. So for this first one here, it's going to be 2 times 2 times 3. Now I'm going to write down these factors underneath the proper column. Well, there's no 2. There's a 3, so put it right there underneath that one. There's an extra 3, so I'll put it to the side here. And now there's a 5, so I put that over here because there's no other 5s to line up with. And for this one over here, I have a 2, so I'll just line up this first 2 here. And then I have a 5, so I'll line it up underneath this 5 right there. And there's another 5, so I'll put it over there. And see if we line these up, I get 2 times 2 times 3 times 3 times 5 and times 5. And if you take a moment to multiply all this together, we get 900. And that's going to be your LCM. Find the LCM of 12, 45, and 50. Again, we can only do 2 at a time. Let's do the first 2.
Let's clear our display, press the math key, right arrow, then the up, and then up again. Notice LCM is highlighted. You could have also selected this by just pressing 8. But let's just press enter. Now let's input the 12, comma, 45, close parentheses, and enter. Now let's find the LCM of 180 and 50. Math, right arrow, and 8. Let's input the 180. There it is, comma, 50, close parentheses, and enter. So the answer is 900.
Now I need to take a moment to warn you about something. A lot of students erroneously want to find the LCM, so they just multiply our numbers together. You go, hey, yeah, 12 times 45 times 50, and that's going to be my LCM. And in fact, that does happen quite a bit, but not always. In this case, what would your answer be? So it'll be 27,000, which is a multiple, but it's not the lowest. And see, the LCM is the lowest or least, the smallest common multiple between these three. So use the procedure that I gave you or the calculator to find the answer. A digit is a symbol used to represent a number and is used in combination with other digits to create other numbers. Now, the digit we're most familiar with are the Arabic numerals. They're right here. And a good way to remember them is, well, they're right here. They're the number keys on the calculator. So what they are. The digit sum of a number is found by adding together the individual digits used to create the number. Now we can see this in this example. 351, the digit sum is you just say 3 plus 5 plus 1, the answer is 9. And I think, well, why do we need to learn this thing? It's going to become very handy very soon. A number is said to be divisible by another number if it can divide into it exactly. There is no remainder. Numbers are divisible by all of their factors. An even number is any whole number that is divisible by 2. 0 is considered an even number. Numbers ending in 0, 2, 4, 6, and 8 are even. An odd number is any whole number that is not divisible by 2. When divided by 2, the remainder would be 1. Numbers ending in 1, 3, 5, 7, and 9 are odd. Yeah, but not as odd as I am. Oh, sorry. Numbers divisible by 2. A number is divisible by 2 if it's an even number, or it ends with 0, 2, 4, 6, 8. So if you look at a number like this, for example, you can look and go, hey, I know I can divide 2 into it because it ends with an even number, 8. Number is divisible by 3. A number is divisible by 3 if the digit sum is also divisible by 3. So if you add all these digits up, 7 plus 0 plus 2 plus 2 plus 1, we get an answer of 12. And see, 12, if you add those digits up, 1 plus 2, the answer is 3, which is obviously divisible by 3. So if you have a number and you can just add up the digits and that result is something you can divide 3 into exactly, then the original number is also divisible by 3. Numbers divisible by 5. A number is divisible by 5 if the last digit is either a 0 or a 5. So looking at this number, oh, that's divisible by 5. You just know it because it ends with a 5. Numbers divisible by 6. A number is divisible by 6 if it's divisible by 2 and at the same time it's divisible by 3. So you apply those rules. So something like this was, well, I know 2 goes into it because it ends with an even number, 4. Now let's find a digit sum. 2 plus 3 plus 3 plus 4 gives us 12. And 3 will go into 12. So, because both 2 and 3 will divide into this number, we know 6 will divide into it. Numbers divisible by 9. The divisibility rule for 9 is just like the one for 3. You take the digit sum, and if the result is a number that 9 will go into, then the original number will also have 9 as a divisor. So if you go 5 plus 2 plus 4 plus 1 plus 6, that digit sum is 18. And 9 will go into 18. Again, if you're not sure, just do the digit sum again. 1 plus 8 is 9, and 9 will go into 9. So it's actually a very straightforward rule. And finally, we want the divisibility rule for 10. Probably the easiest rule for us is the divisibility rule for 10. And that is as follows. If the last number is 0, 10 will go into it. It's the easiest one to remember. So 490 is divisible by 10 because it ends with a 0. I want to let you know that there are other rules for divisibility, but I just find that they're either just too complicated to remember or just too hard to use, and they're not really asked that often on tests. So if you just use the rules I presented to you just right now, you should be fine. Now that we have these divisibility rules, finding the prime factorization of a number is much easier. So let's talk about the basic strategy for this. For our first rule, we try to find a number that will split another number and it will divide it into numbers that are equal in size to each other or close to a size as possible to each other. What I mean by that is with 16, I would not try 2 and 8. See, 2 small, 8's kind of big. I would try something like 4 and 4, they're more even. Something like 50 over here, I would not try 2 and 25 as my first choices. I would try something closer to each other in size like 5 and 10. Now, again, you can try 2 or 25. That's fine. It'll always work. But I'm trying to give you a strategy that will minimize your work, make things go faster. Rule number 1 is fine for smaller values that you can mentally factor. I mean, 16 was easy, 4 times 4, or 50 was 5 times 10. But if you're presented with a rather large number, factoring mentally is kind of difficult. So what you want to do is use the rules of divisibility to try to take out the largest number you can. So you would try numbers like 10, 9, 6, 5. Try to use those rules first. And then if you kind of get stuck, then yeah, of course you could always use, try to use 2 and 3. But it's always worth your while to try a larger number first. Now keep factoring the branches on your factor tree until you can't do it anymore. Now you may have to use larger primes, like 11, 13, 17, and so on. If you're allowed to use a calculator, then use that to help you do the divisions. And finally, the last step is just display all the primes in a row, and that's your prime factorization. Again, you may have to use the exponent notation, and that's fine. In step 3, you're asked to take a guess, like 11, maybe you can divide 13 into it, or 17. The question comes up is, well, when do you stop? But you can just keep dividing and guessing forever. Well, the next test helps us with this. The prime factor test. To find candidates to use to find the prime factors of a number, you only need to try those that are less than or equal to the square root of the number. This test can be pretty handy. Instead of trying to guess every single possible prime before a number, just try those that are up to the square root of a number. So a lot of the guesswork is eliminated. For example 9, I want to find the largest possible number that I can use to try to factor 221. Well, according to the prime factor test, what should we do? Well, let's take the square root of this number. What do we get? Well, just punch it in this calculator, and it's not an exact answer, so it's approximately equal to 14.866 and a bunch of other stuff. So what's the biggest prime number that's equal to or less than 14.86? Well, 13 would be the answer. So that's the biggest I need to go. So now let's actually try to find the factors of 221. So now let's try our divisibility rules. How about for 10? Well, it has to end with a 0. Nope. So this is gone. How about 9? Well, we need to find the digit sum. 2 plus 2 plus 1 is 5. 9 does not divide into 5, so that's gone. And by the same token, that's the same rule for 3, so that doesn't work. The rule for 5, it must end with a 0 or 5. No, so that's not there. 2, well, it has to be an even number at the very end. Nope, so that doesn't work. Now, because 2 and 3 did not work, 6 does not work either. So that's gone. So now we need to try other prime numbers. So now I'm going to divide 221 by other prime numbers in the calculator. What do we get? Well, divide by 7, you get something that isn't an exact answer. Same thing with 11. Ugh. But by 13, we get exactly the number 17. So aha! So that means we can do a little factor tree and we get results of 13 and 17. Now both of those are prime numbers, so we're done. The final answer is 13 times 17. For our last example, we have this number, 1,176. So let's go through our strategy. Well, mentally I really can't factor immediately into different things, so I'm going to now try to figure out, well, what's the biggest thing I can kind of take out of this thing? Well, it's even, and does 3 go into it? Let's actually add up the digits. 1 plus 1 plus 7 plus 6 is 15, and 3 goes into 15, so 3 goes into it, and 2 goes into it, which means 6 goes into it. So I can take a 6 out. Now using a calculator or by hand, you get 196. Now I can continue splitting the 6 easily. That's just 2 times 3. You're done there. Now, here, well, this is an even number, so I know I can take a 2 out, so let's just take out the 2, keep things simple. And that will leave you with 98. Well, 98 is also still even, so I can take out another 2. And you would end up with 49. And 49 is just 7 times 7. So let's write those down. So this is the factor tree for this number. So now let's write the prime factorization. And that's going to be, well, let's put in order. So you're going to have 2 times 2 times 2, and then we're going to have times 3, and then times 7 times 7. And you can abbreviate this by just going 2 cubed times 3 times 7 squared. And there's your prime factorization. For question number 1, we're asked to find the factors of 52. We want all the factors, not just the prime ones. So definitely 1 is going to work. So 1. Let's use a factor tree to help us find the others. Well, 52 is even, so there's a 2, and I will get 26 left over, so that's going to be one of the factors. 26 is even, so I can take another 2 out, and I'm left with 13. And that's as far as you can go. But again, I can use a combination of these to find factors. So 2 times 2 is 4. So let's put a 2 first, and then there's a 4. 13, definitely. 26. And 52 itself is a factor. So here are all my factors of 52. Question number 2 asks, are the following numbers right here prime, composite, or neither? Well, let's find out. 0 is going to be neither. It's not prime, not composite. It won't work. It doesn't follow the definitions of either one of those. 2 is prime. We talked about this earlier. And in fact, it's the only even numbered prime. You know that? 6 is composite because I can think of several factors that'll give me 6. 1 times 6, but also 2 times 3. That's 4 factors. 29 is prime. Why? Well, because only 1 times 29 would work. Nothing else would. Over here, 1 is neither. It's not prime. 2 is the smallest prime. It's not composite. 3 is prime. Only 1 times 3 will work. And finally, over here, 27 is composite because I can think of several numbers that multiply together. They'll give me 27. 1 and 27, 3 times 9, and so on. For question number 3, we're asked, find the GCF, the greatest common factor, of these two numbers. Well, what should we do? How about finding the factor trees of each one? Well, let's see. 60. Lots of different ways we can start this off, but again, let's try to find numbers that are kind of big and close in size to each other. So 10 and 6 will work fine. Put 6 and 10. I can break up 6 as 2 and 3, and 10 is 5 and 2. I won't circle them because I'm going to do something in a second. Let's factor 75. So it ends with 5, so I can take a 5 out, and I would have 15 left over. I mean, you could also have done 3 and 25, doesn't matter really. This breaks down into 3 and 5. Now, for the greatest common factor, well, look what we have left over. I want to find numbers that match. Okay, well, there's 2 here, no, there's a 3 here, and there's a 3 and 3. And there's a 5 here, and a 5 there. 3 times 5, 15. So actually that is your greatest common factor. Now we want to find the GCF of these 3 numbers. 180, 540, and 1200. And I took the liberty to create the factor trees. And if you notice carefully, I circle the ones that have matches. The 3 and a 3 and a 3, 2, 2, 2, another 2, 2, 2, and there's a 5, 5, and a 5. I put them all together, and the answer is 60, and that's going to be our result. By the way, you can just input these three numbers in the calculator, use the GCD function, of course do 2 at a time, and you'll also get the same answer. Problem number 4 asks us to list the first 6 multiples of these two numbers. And here they are. Again, you can use your calculator, use the techniques I gave you to do this, or just do it by hand. You can just go 4 times 1, 4 times 2, 4 times 3, 4 times 4, and so on. 15 times 1, 15 times 2, 15 times 3, and so on. And that's how you can get the multiples of numbers. For problem number 5, we want the lowest or least common multiple of 9 and 30. Well, I start off by doing the factor trees, and let's continue doing the column approach method. So over here I have 3 times 3. Here I have a 3 also, but I also have a 2 which I can't line up directly underneath the column, so I'm going to put it out here. And then there's a 5 over here. So now we line them up. So I get 2 times 3 times 3 times 5, and that gives us 90. And that's going to be our answer. Now let's try the next one. You want the LCM of 8, 14, and 20. Again, I already started off here to save a little bit of time. And I want to create the column approach method for this. I'm going to have 2 times 2 times 2. And over here I have a 2. I have something for the 7, so that's going to go out here. And then I need to, there's a couple of 2's here. 2 times 2, but there's a 5 thing, so I'll just put that out there. It doesn't matter the order. It doesn't have to be in numerical order. And again, we use the column approach. So there's a 2 right there, and there's a 2 right there, and a 2 over here, and then we're going to have a 7, and then we're going to have a 5. If you multiply all these together, you get the answer of 280 is the LCM. Question number 6 asks, are the numbers 56 and 165 relatively prime? That means they have no factors in common. Well, let's see. I created the factor trees for them. Here we have 2 times 2 times 2 times 7. That's the prime factorization of 56. The prime factorization of 165 is 5 times 3 times 11, not counting order, of course. And if you notice carefully, none of them have factors in common. So yes, they are relatively prime. For our last question, number 7, we're being asked to find the prime factorization of some numbers. For 63, we can break it down like this. So our final answer is just going to be 3 times 3 times 7. Again, you can also just write it as 3 squared times 7. It doesn't matter. For this next example, yeah, it ends with 0, so I know I can divide it by 10, but actually, if it ends with 2 zeros, that means 100 will go into it. That's a little something new I'm going to throw at you. So actually, I can break this down into 11 times 100. Now, 11 is prime. Let's break down 100. Again, it ends with 0, so I know 10 goes into it, and it's 10 again. And then I can break these down as 2, 5, 2, and 5. So the prime factorization is going to be 2 times 2 times 5 times 5 times 11. You can also rewrite this as 2 squared times 5 squared times 11. For our last number, we want the prime factorization of 391. So let's try to think of some numbers that will go into it. Again, it's kind of big, so it's not obvious for me. It's not even. I know 2 doesn't go into it. If we add up the digits, we get 13, so 3 doesn't go into it, and 9 doesn't go into it. 6 won't go into it because 3 and 2 don't go into it. Doesn't end with a 5 or 0, so 5 doesn't go into it. It doesn't end with a 0, so 10 doesn't go into it. So we should now try taking the square root of this number. Let's do that next. So the square root of 391 is equal to what? Well, break out the wonderful calculator, and I did this a little earlier, and it's going to be 19.77 and change. So if I'm going to start guessing some primes to divide into it, I will not go past 19. There's no need for that. So you can try 7, so go 391 divide by 7, it's not going to work. 11, that's not going to work either. 13, not going to work either. Finally, I try 17 and it does work. So what we're going to do is you can divide 391 by 17 and you're going to get 23 as an answer. So those are actually the only two that will work for this. So they become the prime factorization for your final answer. You can just write it like that. That's it. Well, we've reached the end of this lesson. Whew. I hope I was able to help, but if you have any questions, please don't hesitate to email me at this address right here below. And with that said, this is Luis Anthony Ast saying, keep studying. Bye-bye.